Question 3.1. Write an equation to use state symbols for reaction with enthalpy change equal to the standard enthalpy of formation for CF4 in this case state. So there's only two key rules you have to remember for the standard enthalpy of combustion or standard enthalpy of formation. With formation, that's what we're forming. So that's what it means. So we're forming CF4 and you just draw an arrow to it. That's the only tricky part for it, because then the rest of it is pretty simple. Well, carbon by itself as a solid, and then F2 fluorine, and then 2F2. That's also slightly tricky, but the hardest part is understanding that standard enthalpy of formation. We write down what we're forming and then draw an arrow to what we're forming. That's it. That's it. I'll explain why CF4 has a bond angle of 109.5 degrees while CF4 is tetrahedral. Actually, it's not, is it? Is it tetrahedral or not? I'm not sure, but it doesn't want us to say that anyway. It wants us to talk about around the carbon. Around the carbon, there are four bonding pairs of electrons and no lone pairs of electrons. Electron pairs repel to be as far apart as possible. Electron pairs repel each other equally. Electron pairs repel each other equally. That's in the question 3.2. 3.3, calculate standard enthalpy of formation of this, and we're given the enthalpy of change. Well, formation data, it says it once, twice, 3 times, and also that just that little f tells me it's formation data anyway. So it should be pretty clear that it's formation data, not combustion data. So delta H is equal to enthalpy of products minus reactants. Whereas if it was combustion, then it'd be reactants minus products, but it's not, it's formation. So enthalpy of products minus enthalpy of reactants. So we know delta H is minus 2889, and that is equal to enthalpy of products. Well, what we're producing 2 CF4, so 2 times by CF4, which is 6 minus 680. That's the enthalpy of that, minus 680, plus 6HF, plus 6 times by HF minus 269, minus enthalpy of reactants, well, C2H6, well, that's what we're trying to find, plus 7F2, which is 0 because it's a single element. Sometimes it might not give you F2, its enthalpy, but you'd be expected to know is 0 because enthalpy of any formation of any single element is 0. So plus 0. So we get minus 2889 equals, actually let me check if yeah, so 2 times by minus 680 plus 6 times by minus 269 should be correct. Minus 2974 minus C2H6. That's the tricky part. Then we add C2H6, therefore we get C2H6 equals minus 2974 plus minus 2889. Minus 2974 plus minus 2889. So what we're going to do is we're going to do minus 2974 plus 2889, sorry. minus 2974 plus 2889, which will give us minus 85. Therefore, the answer is minus 85 kilojoules per mole to power minus 1. 3.4. Methane reacts violently with fluorine according to the following equation. Some mean bond enthalpies are given in table 3. Students suggested that one reason for the high reactivity of fluorine is a weak FF bond. Is the student correct? Justify the answer with a calculation using these data. Well, because it's mean bond enthalpy, delta H equals energy, bonds broken minus bond energy required to break bonds minus energy released new bonds form. So delta H is minus 1904. Energy required to break bonds. As energy released new bonds form. So energy required to break the bonds. So it's going to be CH4. Now what does that mean? If you draw out CH4, methane, and that's what I would also recommend for these type of questions, draw out the molecule so you can see how many of the bonds. So in this case, CH4 is times by 4. This is pretty simple, so you wouldn't have to probably draw a shape of molecules, but they do get more complicated, especially in A-level papers where they love to ask questions about mean bond enthalpy, and they give you very complicated compared to this compounds or elements. So it's going to be plus 4F2. Well, if we draw out F, it's just FF, and we've got 4 of them. So plus 4F minus energy released from new bonds are formed minus CF4, same thing as CH4. It's going to be 484 times by 4 plus 4HF, 4 times by 562. Now the calculation happens. Minus 1904 equals 4 times by 4, 1, 2, 1648 plus 4 FF minus 484 times by 4 plus 4 times by 562. 484 times by 4 plus 4 times by 562 minus, so minus 4184. So we get minus 1904 equals 1648 minus 4184. So 4FF minus 2536. So we get 4FF minus 1904 plus 2536 equals 632. 632 divided by 4 will give me 158. Therefore, FF equals 158 kilojoules per mole to power minus 1. So, okay, now this is a bit of a weird one. It doesn't actually want us, well, I did want us to calculate it, but it really wants an explanation. So I guess like 3 marks for the calculation and then 1 mark for explanation, or 2, I don't know. But the explanation, well, if we compare them, what we just worked out for fluorine compared to everything else, well, it's significantly less than the CH bond enthalpy and the CF mean bond enthalpy and the HF mean bond enthalpy. So what we can say is what is it going on? Why is it going forward for? Why is it going upwards for? What is going on? Okay. But what I was going to say is that the FF bond enthalpy is much less than the CH bond, or any of these covalent bonds, CF or HF. And as I just have to draw it, as FF bond energy much less, I'll just say much less than CH, CF, CF, HF, therefore weak FF bond. Because that's what the question was saying. Student suggested that one reason is a weak FF bond, and therefore, oh yeah, we need to also say student is correct. And that is the end of question 3.